Hello, class. All right, so we're going to look at a very simple circuit that consists of nothing except for a battery, a resistor, and the wires that connect them. I drew this looking somewhat like a battery. More often, it's written symbolically like this, where you have a long line and a smaller line, where the longer one represents the positive terminal and the smaller one the negative terminal. So this terminal is at a higher potential than the lower one. Now if we look at the electric fields go from high potential to low potential. Now, if we set up this battery, the current is going to flow from the positive terminal to the negative terminal. So when I say that current is going to flow, in this case clockwise, what we're talking about is something called the conventional current. So we consider a positive charge, let's say a charge dq, which is a positive charge, that is flowing clockwise. So, the direction of the current is the direction a positive charge would go. Well, we know in reality, the electrons have a tendency to move in the opposite direction of the current. So if we just ignore that, just imagine positive charge flowing through this circuit. In this case, it would be going clockwise. So if you look what's going on inside the battery, we have this electric field going downwards, and positive charge, so the electric force is downwards inside the battery. And so but the charge is moving in the opposite direction of the electric force. And so the battery has to do work on that charge as it flows, through the battery and through the circuit overall. And that depletes the battery. So the battery has stored chemical energy. We're considering, just a traditional battery. There's other ways you could achieve the same thing. Well, let's just stick to the basics. A normal battery that you would put in some electrical device. And so it's turning chemical energy, it's expending chemical energy and putting that into the charge. So the charge would have a low amount of energy here. After going through the battery, it's at a higher potential. So it has more energy after it passes through the battery. And of course that comes at the expense of the chemical energy stored in the battery. And when it flows through the resistor, it's going to lose energy. Now, what about the wires? Again, insignificant. So we just ignore any kind of energy loss through the wires because, like say this is a 100 ohm resistor, the resistance in the wires would be like milliohms at best. So, completely insignificant. And another thing, if you buy like a commercial resistor that's say at labeled 100 ohms, if you actually measure it, you're not going to read exactly 100 ohms. We typically don't have too much precision in these things anyways. So we're totally justified in ignoring the wires themselves. All right. So let's look at this charge dq. Say let's identify a point near the lower terminal of the battery. Let's call that point A. And near the upper terminal, we'll call that point B. And there's kind of two approaches that we can take to analyzing what's happening in this circuit. One is conservation of energy. So the energy supplied by the battery we know when charge flows through a resistor, energy is dissipated in the form of heat. And overall, we establish a steady current. Like if you set this up, there's a certain current in this wire, and you leave it and it's going to remain, at that value as long as the battery can hold up. And so we have a steady current. Energy is conserved here. And so let's look at, just what's happening. We go through the battery. The energy supplied by the battery has to equal what is dissipated by the resistor. So let's say in a time dt, an amount of charge dq flows through any part of the circuit. So we can identify, let's just look at this line here, how much charge passes that line. That would be dq. You can look at any part in the circuit that the current is steady. So through like any part of the circuit. Now, going through the battery, we write down a few equations here. So remember that change in potential energy is equal to the charge times the change in potential. So the battery has a certain charge, a certain potential difference between the terminals. Like if you have a 1.5 volt battery, that would be delta V. Now the rate that power is dissipated by a resistor, in general power is current times voltage, but for a resistor we can also apply Ohm's law. So that would be I squared R. So that's the rate. So that would be, let's actually write it this way. And so we're looking at a small interval of time dt. So for the battery, instead of delta U, we can say du is equal to the amount of charge is dq, and let's say V is the potential of the battery. So that's for the battery, and the rate that energy is being dissipated, so here, let's say battery, or let's just say dUB. So this is supplying energy to the circuit. Now if we look at the resistor, that's dissipating energy, so we have a minus sign, so that'd be minus I squared R dt. So that would be for the resistor. And so overall, if we add this up, we have to get 0. So we have, say, V dq, just to save room, dq, just from the definition of current, dq is I dt. So let's write that down because I'm kind of near the bottom of the board here. So we have dq times V. So we have, like, say, V, we'll put that first, and then we have times I dt plus the energy being dissipated by the resistor. So that'd be minus I squared R dt, and that equals 0. And we can basically divide by I dt here. So we have V minus, we got rid of one I, and we get rid of the dt. And so we get this result that, let's solve for the current. So the current flowing through this circuit is just V over R. So V is the potential difference between the plates of the terminals of the battery. R is the resistance of the resistor. Very simple circuit. We analyze this using conservation of energy. Now, very often, the potential difference between the terminals of the battery, that is a name, that's called the EMF, or electromotive force. The symbol is this kind of E-looking thing. This is electromotive force. And it is defined as, we write it down as an equation. T is D. So it's kind of like this equation. It's defined as the change in energy, or the work done. That may be a better term. Say the battery is doing work on that charge to force it to go against the electric field. So the EMF is defined as the amount of work it's doing on a given charge dq divided by that charge. And you can see the units are joules over coulomb, which equals volts. And so we often use electromotive force and voltage interchangeably. They have slightly different definitions. You know, the EMF is defined in terms of the work done on a charge, where the potential difference is given by the line integral of the electric field. But basically, in practice, they're the same thing. So it's often written this way. The current is, for batteries, you can use either voltage or EMF. Doesn't really matter which. Okay. Now this is the conservation of energy approach. And this is a very good way of doing, it's not necessarily the easiest way to look at this circuit, but it's a very good way to do so. But there's another way we can do this. And let's erase this. And let's look at the idea of electric potential. So, actually, let's say we have a switch here. And then we flip the switch, closing the circuit. So if the switch is open, nothing is happening. Current can't flow. It has to be able to complete a loop in order to have a current. That cannot happen here, and so nothing's going on. When you flip a switch, current is going to flow, and this flow of current involves actual moving charges. They have to actually accelerate. And so the current can't just instantly go to, we know that we're going to have a current. But it can't instantly go from 0 to E over R just because of inertia. There's actual charges that are moving around here. And we'll actually see later another way of looking at this from the perspective of electromagnetism, where we don't even have to look at the kind of moving charges themselves, but there's a reason why the current can't just instantly jump from one to the other. However, it happens extremely quickly in a case like this. If you just have a circuit like this, you wouldn't really notice it. It would appear to just jump instantly. And then we're going to have a very steady current flowing in our circuit. Like, say you have a current of 1 amp, and you leave the room, come back a few minutes later, you still have 1 amp going. It's a very steady current, nothing is changing. And in cases like that, we have something called the loop rule. In cases like that, potential is very well defined. So electric potential, remember that only applies to conservative systems, and that is what we have here when we have the steady current flowing. You have to be a little bit careful, like if the current is changing, that kind of complicates things, and we can no longer say that we have a conservative system in that case. So let's, but in this case, we're fine with the idea of electric potential. And this gives us kind of an easier way to approach this problem. Although I like showing both ways because this idea of potential, it's actually very tricky when you're talking about electric circuits. And it's not always valid. So we have to be clear on that. So anyways, the idea of electric potential, remember it's the potential at any point in the circuit has to be constant. So like, let's just say this is the negative terminal. That's where the potential is going to be lowest. Let's just say that the potential here is 0. You know, it has to remain 0. And so if you look at a charge as you just go around the loop, once we finish the loop and get back to point A, we have to be back to 0 potential. The potential has to be 0 here. It can't change if we go around the loop and get back where we started. So if we just picture a charge moving through here, we have this charge gains energy going through the loop, or there's a gain in potential going through the battery. So going through the battery, so for a charge dq, we have delta V for the battery would just be equal to the EMF. And delta V for the resistor, or the potential drop across a resistor, is just IR. And so the change in potential is going to be minus IR. If we go like in the direction the current's going, we're at a lower potential after going through the resistor. And so these are the only two potential changes we have in this circuit, the battery and the resistor. Now if we had resistance in the wires, we could take that into account very easily by just treating them as resistors. But in this case, that's negligible. And so there is something called the loop rule that we can apply to circuits, which says the sum, well, I'll just write it, sigma V equals 0. Or sigma delta V if you want to, just the sum of all the potential changes in any complete loop has to be 0. So you have to, if you start and end at the same place, if you add up all the changes in potential, that sum has to be 0 because you have to get back to where you started. And so that leads very directly to epsilon minus IR equals 0, which we can solve and get the exact same thing. So again, somewhat easier approach using this loop rule. All right. I want to talk about one more thing relating to batteries, and that'll be it for this video. We're going to keep this one kind of short, just to introduce the basic ideas. But again, this loop rule, it depends on the idea of the electric potential, which only makes sense for a conservative system. So we have to be a little careful in using it. Even though in practice it doesn't cause problems, but it can be a little tricky to justify using it in some cases. So I like the conservation of energy approach a little bit more. But let's look at this battery, and we say there's an EMF between the terminals. And you may know real batteries actually do a pretty good job of supplying the right voltage. Like if you have a 1.5 volt battery, and it's brand new, it's probably going to supply 1.5 volts of energy, or potential difference. As it gets older, though, you'll notice potential across the terminals drops a little bit. They do a pretty good job, but eventually, you'll lose some of that. And we can model a battery this way. The EMF of the battery is going to be constant. So battery has a certain EMF. Like if you have a 1.5 volt battery, that is the EMF regardless of the age of the battery. But we say the battery has an internal resistance. So like this combination here is our battery. And like the dashed outline, that is our battery. And so it consists of the EMF here and that internal resistance, which is inside the battery. So again, this is point A, this is point B. And so if you look at the potential between points A and B, let's start at point A. So we have VA. There's a current I in this circuit, in this loop. So if we start at VA, going across the terminals, we get plus E, the EMF. But then we have a voltage drop through that internal resistance, and that brings us to point B. And so here we didn't consider an internal resistance. In this case, we had VB minus VA is equal to epsilon, but a more realistic battery, we'd have VB minus VA equals epsilon minus IR. That's a lowercase r for the internal resistance of the battery. So if you run a significant current through this battery, if it has an internal resistance, the potential between the two ends, that's what you'd measure. If you hook a voltmeter up between the ends of the battery, you would measure that potential difference. You could get something less than the EMF of the battery. And the older the battery gets, the more significant that becomes. So yeah, VB minus VA, that's what you would actually measure between the terminals of the battery. And I think we'll stop this one here. And we can definitely expand on this idea of circuits. For one thing, we just have a battery and a single resistor. We're going to consider what if we have two resistors. And there's also, we can consider more complicated circuits. Like say we have a battery. And say we hook up wires like this. We have two resistors that are hooked up like this. So you can have these wires, they form a junction here where one wire goes this way, the other goes that way. And so we can consider more complicated circuits, and we will. And we're also going to consider, what if we put a capacitor in our circuit? That gives us some interesting results. But that'll be it for this video.